In this video, I'm covering 10 exercises related to chapter 20. As you go through this video, you may want to stop the video when you see the question, answer the question on your own, and then play the video to see my answer. So first question, predict the major product of the following reaction. So we have reaction of side chain, a vinyl group on benzene ring. So that's styrene. So reaction of styrene with hydrogen chloride. And so reaction proceeds in such a way that less substitute carbon forms bond with hydrogen to give benzylic carbocation. It's much more stable compared to alternative primary carbocation. And then reaction with chloride anion with the nucleophile gives the final product. And then you match that product with one of the four possible answers, and correct answer is A. Note that C would be completely wrong because this is not Markovnikov selectivity where we would have more versus less substitute carbocation. This is effect of benzene ring, and effect of benzene ring is such that we effectively get only one product. We don't get mixture of two products where one is predominant, the other one is obtained in smaller amount. We effectively get none of the less substitute chloride. Next question, consider the following reaction sequence. So we have anisole and then nitration to give compound A, and then catalytic hydrogenation to give compound B. So obviously what is structure of B? So first, nitration of anisole. Nitration of anisole gives mixture of ortho and para isomers. Obviously, all four possible answers that are given here are ortho isomers. That means you should consider what happened with ortho isomer, ortho nitroanisole. We will ignore para anisole. So that's compound A, ortho anisole, and ortho nitroanisole. And then catalytic hydrogenation reduces nitro group to amino group, and so that's compound B. And then you match it with four possible answers. You can see it matches D, so D is correct answer. Next, which of the following reactions does not proceed in a good yield? When we consider aromatic substitution reaction, there are two main reasons why some reaction that is shown would not proceed in a good yield. One is effect of substituent. That substituent may be deactivating, and then reaction will not proceed because aromatic ring is not reactive enough. For example, Friedel-Crafts alkylation and acylations will not proceed on deactivated benzene ring. Second possibility is that as written, reaction will not proceed because the existing substituent directs substituents into different location, different position on the ring, and not where is indicated. So if you consider A, this is activating substituent, methoxy group, it's ortho-para directing, this reaction would proceed quite well, this Friedel-Crafts alkylation. We may probably get polyalkylation, but nonetheless this proceeds as written. B, bromination of phenol, yes, that would proceed very well. Hydroxyl group is ortho-para directing, bromine comes in para position, so that works. C, nitration of chlorobenzene. Problem here is that chlorine as substituent is ortho-para directing, and we have meta-chloronitrobenzene as the product. So that reaction would not proceed in good yield. This is not meta-directing substituent. And finally, toluene. Methyl group is ortho-para directing, so nitration of toluene gives 2,4-dinitrotoluene. That would proceed in good yield because those are ortho and para nitro groups. So correct answer is C. Nitration of chlorobenzene will not proceed to give meta-chloronitrobenzene in good yield. Next, which of the following reaction sequences is suitable to convert benzene into benzonitrile? Well, this is a multiple choice question. It should take a little bit of time to figure out the answer. Basically, you're supposed to analyze each reaction sequence one by one, figure out which are not reasonable and why, and then which is remaining sequence that will result in formation of benzonitrile. So let's consider sequence A. First step is bromination of benzene. That proceeds quite well to give bromobenzene. But second, reaction with potassium cyanide would not react because that should be SN2 reaction with nitrile or cyanide anion as nucleophile. So mechanism should be SN2, but SN2 reactions don't work on sp2 hybridized carbon of benzene ring. So there will be no reaction. And so this does not work. B, first step, reaction of benzene ring with sodium amide in presence of ammonia as solvent at minus 78 degrees Celsius will not work. Those are conditions for preparation of benzene if benzene ring carries leaving group like chlorine or bromine. But in this case there is no leaving group, so there is no reaction. And so B is not reasonable sequence either. C, first step is nitration. That works very well to produce nitrobenzene. But second step would be diazotation reaction, except that substituent is nitro group, not amino group. Mixture of sodium nitrite and hydrochloric acid will convert amino group into diazonium group. So this is not going to work. And finally, we have sequence D. Obviously, that must work. So first, reaction of benzene ring with nitration mixture gives nitrobenzene, then reduction, catalytic hydrogenation gives aniline, and then diazotation gives corresponding diazonium salt, and finally reaction with copper cyanide gives benzonitrile. So that's correct answer for D. Now we have 3 questions that refer to this reaction shown here. So orthobromonitrobenzene reacts with sodium amide in ammonia. So what is the reaction mechanism? The reaction mechanism is nucleophilic aromatic substitution, because under these conditions, sodium amide and ammonia eliminate hydrogen bromide from benzene ring to give benzene as intermediate. And benzene is an intermediate in nucleophilic aromatic substitutions. And that also answers next question. Question number 6. The reaction intermediate is benzene. And then reaction products are benzene reacts with a nucleophile, of course nucleophilic aromatic substitution, and nucleophile can add to either carbon of the triple bond. And so addition to either carbon of the triple bond will result in formation of disubstitute benzene, and that means a mixture of ortho and meta isomers. We already have nitro group there, and triple bond is next to it, so it's going to be ortho and meta isomers. Again, it's the best to use pen and paper when answering questions like this, rather than trying to just figure out answer by inspection. Next question, what is the structure of the reaction product? So now we have benzene ring with 2 hydroxyl groups and sulfonation reaction. So 2 hydroxyl groups are orthopara directing. We can indicate one in blue, one in red, and so one in blue, its directing effect is orthopara, shown as filled blue circles, and one in red, shown as empty red circles. We can see that their directing effects overlap. They will direct incoming substituent, incoming sulfonate group into orthopara positions relative to themselves, same 3 positions. Now, answer C is not correct because incoming sulfonate group would be between 2 hydroxyl groups, and there is steric hindrance, so that's not favorable. Those are not favorable conditions. So that's not going to be certainly the major product. The major product will be D, where sulfonate group ends up in one of the remaining 2 positions. And either of the 2 shown by block arrows gives the same product, product D. So that's the correct answer. Next question, which synthetic sequence would accomplish the following transformation? So again, you have to consider each sequence in turn to figure out which one is reasonable, and those that are not reasonable, why they are not reasonable. First one, chlorination of toluene gives a mixture of ortho and para-toluenes. And then permanganate oxidation oxidizes methyl group to carboxyl group, but we get mixture of ortho and para-benzoic acids. And product should be metachlorobenzoic acid. So this is not correct answer. So that's not correct sequence. B, we first carry out oxidation of methyl group of toluene to carboxyl group to benzoic acid, and then chlorination. Carboxyl group is meta-directing, so in this case product is actually metachlorobenzoic acid. So B appears to be correct answer. We should still consider C and D just to make sure that we did not miss anything. So C, again, first step is chlorination to give ortho and parachlorotoluenes, mixture of ortho and parachlorotoluenes, and then PCC with heat. Actually, PCC does not affect methyl group. That's pyridinium chloride, pyridinium chlorochromate. So pyridinium chlorochromate does not affect this compound, so there is no reaction. And the fuming sulfuric acid, that one would actually accomplish sulfonation, mixture of ortho and parasulfonations of toluene, and then chlorination would introduce additional chlorine atom. That's completely different compound, so that's not correct. So obviously correct answer is B. Next question, which combination of starting materials would yield the azo compound shown below? So we have azo compound, one substituent is phenyl group, the other one is obviously comes from anisole, so we should consider combinations. And A doesn't look right because in this case you would have addition of aniline to diazonium salt that already contains methoxy substituent, so that would be a different product. B, that looks correct because we have benzene diazonium chloride, and that reacts with anisole. So that appears to be a pair that will give correct product. That's shown here. C also is not correct. We have parachloroanisole with chlorine as possibly leaving group, but these compounds don't involve halogens or leaving groups or anything like that. This type of reactions, those are diazonium coupling reactions. They involve hydrogen as a leaving group. So that's not correct. And D is certainly not correct because it does not involve a diazonium group. So correct answer is B. And finally, a free response question. What is the product of the following reaction? So this is bromination of phenyl benzoate. In this case, we have two benzene rings, and they are attached to an ester group. Note that one benzene ring is attached to carbonyl group, shown here as highlighted in red, and that's the activating substituent. So that benzene ring is deactivated. The other benzene ring is attached to oxygen, and that's activating substituent. So that benzene ring is activated. It's highlighted in green. So benzene ring in green will be reacting, not one in red. And oxygen is ortho-para directing group, which means that it's going to direct bromination into ortho and para positions. Note that this ester substituent is rather large, so ortho positions are going to be hindered, and substitution in para position is going to be preferred. So the major product is going to be result of para bromination. And this completes chapter 20 exercises.